All right, you're recording. Share the screen. Thingamajigger. Okay. What do I want to do here? So I just returned the last two worksheets. You should get a notification or whatever you guys get for that, which means they're all graded and returned, except for the few of you who turned stuff in like 2 weeks late just now. What I want to do today, briefly, because this is not a real class, obviously, I want to go over the last 3 worksheet solutions. All right, so the last lecture I went over the last 2 of them or something. Oi, what's going on here? Now, no one has anything to say. Okay, go away. So I went over the last, or the first 3 worksheets at the end of the last lecture, so you can watch that if you want to see, batching and things like that. Today I'll go over the last 3. So mechanical, optical, thermal, and electronic and magnetic. And then I'll talk about the final exam. All right, some information about that. So this isn't a lot of slides. I mean, I could talk about it for a while. So mechanical properties, this one. All right, so you had this question. All right, or questions, I should say. Using the graph, determine the following for the unknown material. This was in the book, in maybe the strength section. This graph is right from the book. All right. Use the appropriate units and show your work. All right, figure out from this graph of stress and strain, figure out Young's modulus. Okay. Yield strength, tensile strength, maximum elastic strain, and the plastic strain. And I said you should draw on the graph because, well, you kind of have to. At least in one of those questions, you need to draw a line successfully. All right. So, what do? Right, we have these 5 things defined here. Well, you should figure out what they are, where they are, or how you might determine them. All right, you can look in the lecture slides, you can look in the book, right, for these things. Modulus is just the slope of this elastic portion, right? You could also use the inset graph, right? This has been zoomed in a little bit. This is just the elastic portion, right? Ideally, you should get the same answers, regardless of which of these graphs you use. But yeah, they could be a little different. Maybe it's not a perfect graph. All right, so slope is Young's modulus. Find the yield strength, the yield stress. And that goes from where it transitions from elastic to plastic. All right, and there's convention. Some of you use the convention where you found like, 0.002. You could continue the line and figure out where it deviates. That would work as well, right? Or you can draw a horizontal line and see where it deviates, maybe a vertical line, right? So just seeing what you came up with, all right? A lot of these answers, you should be similar to what I get, all right? It's not going to be exact, right? We have different eyes, maybe slightly different rulers, though they shouldn't be. But you should be close. If we took all the answers and averaged them, right, they should be all pretty close. If you're really way off, you did something really wrong. All right, tensile strength, right? It's something like at the top here, right? This at the end would be the ultimate strength. And then elastic strain and plastic strain. Right? And if you look around, you might see a graph labeled like this, right? Where I pointed out in the beginning of that lecture, right? You go up, and if you unload it, if you unload it, right, you're going to recover the elastic strain, but you'll have some permanent plastic deformation. At the end of the line, right, that's the total strain. So if you just subtract plastic from total, you get the maximum elastic strain, right? Some of you just went to the yield and called that the elastic strain, which isn't quite the maximum. When you're pulling on something, right? Okay, you're pulling on it elastically, and then it yields, and you keep pulling on it, and you're getting plastic deformation. Well, you're still getting elastic deformation on top of that. We tend to forget about that, right? So if you calculate elastic strain at the yield, right, it might be slightly smaller than if you calculated it from the total strain and subtracting plastic. It'll be a little different, right, depending on how much you deform it. All right. So again, you can identify where these things are, and then you can print it out and use a ruler, right, or just on your computer like I would do with these things now. And you can use linear interpolation, right? This is a very coarse scale, right? 0, 1,000, 2,000, right? You have to interpolate that. Okay, some of you drew your own scale, which could work sometimes, but for best results, you should interpolate it. All right. So yield strength. All right. It goes up. You can continue the line. Like in this figure, they continue the line. I kind of figure out where does that deviate, right? So this is where it's a little open to interpretation, which is why some people might prefer 0.002 strain, right? Because maybe it's a little difficult to find, right? I said it was right about there, all right? Now, when I measured this, all right, so these are the measurements I have, all right? So if you have this zoomed in or zoomed out, you're going to get different numbers, right? But the ratio should be the same, right? So I measured between 1,000 and 2,000, right? So 2,000 minus 1,000, all right? Plus 1,000 because we're starting from down there. So I measured from there to there. A question? The heck was that noise? Or not? That was a question. I didn't hear it. It doesn't sound like a question. They'll unmute if they want to. All right. So I got 1.39 GPA, right, or 1392 MPA. A lot of you were like 1.7, like really excessively high, even if you're doing something like 0.002 perhaps. All right. And I didn't say find the 0.002 yield strength. I just said find the yield strength. Right? Those are different numbers. All right, Young's modulus. All right. Now, if you did the yield strength first, right? If you did the yield strength first, well, you know that stress, and you know that you can determine the corresponding strain, right? Here I interpolated the corresponding strain, right? And so you get the modules. It was about 200 GPA. All right. I think most of you were right around there. All right. It was something like yield strength. If you're off maybe 100 MPA up or down, that's probably reasonable. If you're getting into 200 or 300, you're measuring something wrong or just plain different. All right. And then tensile strength. All right. That's the maximum stress it gets to. Right. That's the tensile strength. The end is the ultimate strength. So the maximum you get to is tensile. And again, by interpolation, stupid number here, 1.95 GPA or 1954 MPA. Right? So again, you should be close to these numbers if you're being careful about it, and assuming I didn't make a measurement mistake. Right. You'll see down here, we want to find the strain. In those figures, and I believe I pointed this out in the lecture, you have a line here, right? You have this unloading line. This unloading line, right, which is going to be parallel. It's going to be parallel with loading, right? So you get your ruler out, or you draw a line digitally, and you shift it over. You shift it over until you find the ultimate strength there, right? So that line is going to connect to the strain scale, right? And you have a perfectly vertical line at the ultimate strength, right? So you make basically a triangle here. You make a triangle. This would be the plastic strain, and this would be the maximum recoverable elastic strain, right? Which is a little bigger than if you were just measuring this strain here, this 0.007. It's going to be a little different, a little bigger. All right. So total strain. All right, we find the total strain. That one's easy. It's just a vertical line. We find it's 0.077. Right, a lot of you found that number. A lot of you found that number, but that's the total strain, not what quite a few of you called the plastic strain. All right, the plastic strain is from 0 to the unloading line. That's the plastic strain. That was about 0.068. All right. So if you subtract the plastic from the total, you get the recoverable, or the maximum elastic, 0.009. Right. Back here, the elastic strain at yield, right, that was 0.007. See, you can add a little bit more elasticity after plastic deformation. You're still stretching bonds, right? It's not like we stopped stretching them all of a sudden. We're still stretching them. So we add a little bit more to it. So it's about 0.009. Okay. We had question 2. Question 2. If a load of 140,000 newtons is applied to a 0.4-inch diameter cylindrical specimen of the unknown material, A, will the specimen experience elastic and/or plastic deformation? Okay, why? If the original specimen length was 20 inches, how much will it increase in length? I said here in millimeters when the load is applied. Right, so this is unknown material, right? This was unknown material, right? So you're using the numbers you just figured out, perhaps. All right. So, will the specimen experience elastic or plastic deformation? All right. We have to figure out what's going to be the stress. What's going to be the stress on this cylindrical rod? Right. We're gonna load it up, and we're gonna pull on it. And is it going to just stay in the elastic regime, or are we going to go past the yield point into plasticity? Right. So you know that stress is simply force over area. Right. Force, we know it's 140,000 newtons. Right. This wasn't a load in kilograms. It's already in newtons. And the cross-sectional area, okay, it's a cylinder. Right. So it's circular. So pi r squared. So 140,000 divided by pi. Now, it's 0.4-inch diameter, which some of you thought was the radius. So it's 0.2 inches. In radius, we have to convert that to meters, right? Because we want pascals. I mean, you could do this in PSI too if you wanted to. There was a PSI scale here if you wanted to do that. No one's going to do that. All right, so multiply that by 0.0245 meters per inch, square that thing, and you get 1.73 GPa. 1.73 GPa, or 1,730 megapascals. We figured out in question 1, the yield strength was 1.39 GPa. all right? So we're applying a stress greater than yield, right? So it should have plastic deformation, right? But this question, this was a bit of a, I don't want to say a trick question. Again, if you looked in the book, you would have seen this question very similar to this. If you have plastic deformation, well, you had to go through elasticity to get there. You can't have plastic deformation by itself. You have to go through elastic to get to plastic, right? You can have just elastic by itself, but you can't have plastic by itself. So you have both elastic and plastic, right? Slightly tricky question to see if you were paying attention, right? But yeah, if you go through yield and you have plasticity, you also have elastic deformation on top of that, right? This graph that you've measured, right? You found a total strain, you found a plastic strain, there was elastic strain that you recovered, right? So if you go through plasticity, you also go through elasticity simultaneously. All right, so it was both of them. All right, now how much does the rod stretch? Now you might just jump into Hooke's law and calculate that, and then you go, wait a minute, there's plastic deformation too. Hooke's law has nothing to do with that. We have a graph. Right? So you can find 1.73 GPa. You can find the corresponding total strain, right? You can find the corresponding total strain, 0.0168. And we know that strain is delta L over L naught. We know that L naught was 20 inches. Convert that into centimeters or millimeters. Oh, that's millimeters. That's not centimeters. That's a typo there. It's 25.4 millimeters to the inch. Typo, right? And we find 8.53 millimeters. If you just used Hooke's law, which a lot of us might just jump right into because we forgot its plasticity, you're gonna get maybe half of that. Right? You're just gonna calculate the maximum elastic deformation. All right. But you had to use the graph and find the total strain and use that to calculate delta L. Right, so it's about 8.5 millimeters. I mean, you had to be close to that, right? Some of you're very, very close. It depends on how well you measure the strain, right? Are you doing interpolation correctly, or are you just eyeballing it and going, okay, 10, 15, maybe it's 16, right? All right, so that was mechanical properties. That is the last one. Yep, last one. All right, optical and thermal. This is a fun one. All right. So this was a new one. I wouldn't really give this during a class because it takes a little longer to solve in an hour if you're just staring at this. This one you had to maybe do a little research to solve this elegantly. All right. For a glass equilateral prism, right? So these words have meaning, like equilateral, with a base length of 25 millimeters. That thing down there. If you shine a beam of light through it on an optical path that is initially parallel to the base, calculate the following. The glass has an absorption coefficient beta of 5.6 times 10 to the minus 3 and a refractive index N of 1.462. The prism is held in air. Show your work. So calculate the following here. Where's my phone making funny noises? Why are people? Oh no, what the hell? People asking me questions in line at the moment. Hold your horses and wait till the end. All right, so you have all this data. You have a triangle here. All right, you have light coming in here, and it's halfway down, right? It's halfway there. And I drew these little optical lines with little perpendicular things, all right? And this is 60 degrees because it's an equilateral triangle. All right, calculate the red path length x in millimeters, right? So how long is that line? Calculate the exit angle, theta sub e, shown in the diagram. So what's that angle? All right. Calculate the percent reflection of the air glass interface. All right, so how much light is reflected? Calculate transmission along x, accounting for both A and R. All right, so that's one equation right there. Not two separate equations that everyone was making up one. E, calculate the total percent loss due to reflection. Calculate the total percent loss due to absorption. All right. So this was an optics question, and also, do you remember like middle school and high school mathematics? Because a lot of optics is really just kind of geometry and trigonometry questions, which you probably learned years ago and maybe thought you'd never use. All right, sometimes you do in optics. So we can look at this diagram. All right, we can look at this diagram, and I said that the optic path is parallel with the base, and it's intersected here by this third line. So you had to remember this, right? When you have two parallel lines intersected by a third, right? That we have a whole bunch of angles which are equal, right? When these two things are parallel, like this angle and this angle are equal with that, and these angles are equal, right? And that these two angles have to add up to 180, right? So we can look at this diagram. We know that this is an equilateral triangle, so 60, 60, 60, right? We know that this line is parallel with that line, so this has to be 60 because that was 60, right? And this is 90, and we know this has to add up to 180, right? So this has to be 30, right? So it's just a trigonometry problem, right? So we know this angle in here is 30 degrees, right? This incident angle. Right? So how do you find the red path length, right, in millimeters? Well, you have all these angles here, right? We know that this is 60. We know we have a triangle here. We don't know any of these other angles floating around here. So we can use Snell's law, right? We can fill in some of the unknown information to help us find x, perhaps. So use Snell's law to calculate the refracted angle, theta t, right, which would be this angle in here, right? If you rotate this, if you look at it sideways, right, you have incident and transmitted, right, when you look at a Snell's law problem. Right? So that's theta t, right? And if that's 90, then that has to be 90, right? So if we find this angle, we can find theta 1. And if we know those two, the interior adds up to 180, so we can find that one too, right? So we use Snell's law, right? We want to find theta t. We said that it's in air. Here's the index of glass. Here's the incident angle 30. And theta t would be 20 degrees, all right? 20 degrees. Now, there was some more basic trigonometry. I don't think anyone made this mistake this time, but people have in the past. Sine, cosine, and tangent, they only apply to right triangles, right? So a triangle with a 90-degree angle inside. These don't work on anything but right triangles, right? So you can't use cosine on what's an acute scalene triangle, for example. You can't just use sine, cosine, tangent on this triangle. It's not a right triangle. And some people did do that, I believe, right? And, to find, people who were finding x in the past, some people have found numbers which were physically impossible, like finding x bigger than the base You can't have that. That would be physically impossible for that triangle. All right. So you always have to remember the basic laws of math, they still apply to materials problems, right? You can't violate laws of math to solve a materials problem. It doesn't work that way. Right? So path length x, all right? So we know that this is 20, right? Which means that this angle was 70. That angle was 60, which means that angle there is 50, all right? Now you can go and start breaking this up into lots of little triangles. And that does work. It's tedious and annoying. You know, there's got to be something better, right? If we know a dimension and we know the angles, why can't we figure out, you know, X or B or whatever here? And you can, right? You can apply what's called the law of sines, right? Which maybe you learned it as a student, maybe you didn't, right? But we have the three sides of a triangle and the three interior angles, right? So we have A, B, and here X, right? So B and 70 correspond, A and 50 correspond, X and 60 correspond. It's opposite, right? So you have the angle in the corner and the opposite length. And A over sine of A equals B over sine of B equals X over sine of X, right? That's a known law of sines. And so we know A is 12.5. And we know that angle there is 50, right? And we know that has to equal the same ratio as X divided by the sine of the angle of X there, which was 60, right? So we can plug those numbers in, find that X is 14.13 millimeters. Tell me that was not way easier than trying to cut this up into little triangles and finding it that way, which does work, but takes a long time. This is always something good to remember for some types of problems you might run into. All right, so that's 14.3. Now, determine the new incident angle, right, which would be here, theta I, right? With that, you can solve for the transmitted angle, theta T, which then gives us this exit angle, I called it, theta E, right? So we know that this was 50, right? That's 50. Because this is a right angle, the incident angle has to be 40, right? So again, we use Snell's law to find the transmitted angle, all right? So now we have 1.462 sine of 40, right? There was a 1 here, but we divided by 1. Gives us the transmitted angle is 70 degrees. And because this is 90 degrees, the exit angle is 90 minus 70, or 20 degrees, right? So there you go. That was 20. Calculate the reflection. This is just using the reflection equation. So we have air, N is 1. We have glass, N2 is 1.462, right? We know that the equation to calculate reflection is this, right? N squared minus N1 squared divided by N2 plus N1 squared, right? We can plug that in and find that the percent reflection is 3.52%, right, after multiplying it by 100. Right, so 3.5%. Right, this is just like the example in the lecture slides, right, with a slightly lower refractive index, perhaps. Right, so that wasn't difficult, 3.5%. Now, calculate the percent transmission along X, accounting for both absorption and reflection. That is this equation. This is accounting for reflection and absorption simultaneously. It's not that you use two separate equations, right? This is literally how I wrote it. I think in the lecture slides, accounting for both of these. It's one equation. Right? So you've calculated path length X. You found the reflectivity. So you just dump those numbers in with beta, and you get the T 0.86. where the percent transmission is 86%. All right, that was the answer I was looking for. All right. Now, some basic accounting. Right? Remember, you have that TAR equation. Right? There's that TAR equation. Right? It's not literally TAR. You have, T plus A plus R, right? Everything has to add up to 100, or everything has to add up to 1. All right? So with no reflection, the absorption, right, was 100 minus T. But now we have to account for reflection, right? So absorption would be 100 minus T minus N times R, where N would be the number of reflections, right? If we only had one reflection, great. But if we have, 2 reflections, we have to account for that. So the total reflection, all right, the total reflection. Well, how many reflections are there? There's only 2 here, and they reflect the same amount, 3.52%. The index is the same. The mismatch is the same. It doesn't matter if it's going air to glass or glass to air. It's the same reflection, right? So the total reflection was 7.04%. So the total absorption would be 100 minus 86 minus T times 3.52, or 7.04. So the total absorption would be 6.96%, right? And we could add them back up to check. 86 plus 697 plus 704 is 100, right? Some of you got that, or some of you got close to that, and some of you had really, really, really small, weird numbers like 0.0004% or something. Again, if this stuff's supposed to add up to 100, and you're calculating numbers like 86, 0.00004 doesn't make any sense. All right, so this was a summary. Right, again, these are realistic numbers, right? These are realistic values, and these are realistic numbers you would expect, right? In an optics situation. Yeah, you can lose, 10% to absorption or 10% to reflection. But in something like this, you're not going to lose like, 50% or 0.0005%. Those numbers don't make any sense in most realities. All right, thermal problem. A 0.5 meter long rod of aluminum is heated from 25 degrees Celsius to 600 degrees Celsius. If the rod expands 6.64 millimeters, calculate the coefficient of thermal expansion alpha. Show your work. Right? How do you measure thermal expansion? All right, how do you measure that coefficient? Basically a situation like this. You have a sample of material and you put it in a furnace and you heat the material up and you measure the expansion as a function of temperature change. And you use that data to calculate alpha, all right? And part B here, calculate the density, grams per centimeter cubed, of aluminum at 600 degrees C. The room temperature density of aluminum is 2.7 grams per centimeter cubed. Use the coefficient of thermal expansion and calculate it in part 1. So I may have mentioned this, I may not have, but yeah, okay, there's thermal expansion and there's volumetric expansion. If something gets bigger and we make the assumption that the mass doesn't change, then the density will, right? Because density is mass divided by volume. If the mass stays the same, but the volume gets bigger, the density should go down, right? So this is just to illustrate that. All right, so A, solve directly for alpha with the given information. We know that alpha is 1 over delta t times delta L over L naught, right? 1 over, what's delta t? 600 minus 25. What's delta L? It was 6.64 meters, right? What was the original length? Half a meter, right? So plug those numbers in, right? Make sure the units are okay. And you get alpha was 23.1 times 10 to the minus 6th degrees C, which should be a fairly realistic value for aluminum, right? So yeah, you have some rod, it has some original length, half a meter, to 25 C. We heat it up to 600, and we get some expansion of 6.64 millimeters, right? You can put those numbers directly into the equation to calculate thermal expansion. All right, and then B. If we heat something up moderately and we don't expect it to change mass, right? It's not going to boil off into aluminum vapor, right? Then we could expect the density for materials to decrease. If we heat them up and they get bigger volumetrically, then their density should decrease. All right. Now, it's assumed that the mass of aluminum does not change. 2.7 grams of aluminum at 25 degrees Celsius is still 2.7 grams of aluminum at 600 degrees Celsius, right? That might be an assumption we make. The volume does expand though, right? So calculate delta V, and you can use that to calculate the density. Now, we know the density should be lower. I said here, you can assume that delta V is 3 times alpha, all right, or alpha V, volumetric thermal expansion, is 3 times linear expansion. That's a common approximation. So we can look here, and we can figure out that delta V is 3 alpha delta T times V at 25 Celsius, right? We're just substituting here delta V and V naught instead of L, all right? So we can solve for delta V, right? Delta V is 0.0398 cubic centimeters, all right? So the volume at 600 is the volume at 25 plus delta V, where the new volume is 1.0398, right? At 25 C, it's 2.7 grams per centimeter cubed. Per centimeter cubed is 1. So per 1 centimeter cubed. So it's just 1 centimeter cubed for every 2.7 grams. We add the difference, right? So now we've got 1.0398. We know that density is mass divided by volume. The mass was 2.7 grams. Here's the new volume. And we'd find the density decreased to 2.6 grams per centimeter cubed. And that logically makes sense. The mass is constant, the volume is bigger, so the density should be lower. And it went from 2.7 to 2.6. That passes a logical sniff test. Now, you could go further than that and turn that into a general equation for density. Wouldn't it just be nicer to have an equation where we can calculate the density directly, right? So with the same assumption of a constant mass, we can write an equation for density directly, all right? And this is the derivation for that equation, which you may not find in books too often. But you find that density as a function of temperature depends on the initial density, right, and the change in temperature. And here, the coefficient of thermal expansion, right? We can use this equation and we get the same exact answer because it's derived from the first equation we used, right? Rather than using these volumes here, right, we can substitute in mass and density, but mass is constant, so that goes away. And we're left with density terms. All right, so you could derive an equation too. All right, that's that one. All right, last worksheet here. Then I'll talk about what's on the final. So worksheet 11. Anything crazy going on here? All right, so the last one, electrical and magnetic properties. Again, another fun one. All right, the number of electrons in the conduction band, N sub E, may be determined as this exponential equation. N sub E is approximately equal to N sub C, e to the minus Eg over 2 kT, where N sub C is the density of states in the conduction band. And I said here approximately 10 to the 25 per cubic meter. Eg is the band gap energy in electron volts. K is Boltzmann's constant, 8.617 times 10 to the minus 5 electron volts per Kelvin, and T is temperature. For a temperature of 1000 degrees Celsius and a sample volume of 25 cubic centimeters, which I think literally everyone ignored, except maybe like 2 people, complete the table, which again, a lot of you ignored. Show your work. So we have EG, 8.8, 3.4, and 0.01. Now, ideally, this is probably 0, but how do you calculate that if this is 0, right? So we'll just give it a tiny little number, so you get some electrons out of that. B, which material, X or Y, is likely to be the better electrical insulator? Explain your reasoning. All right, so calculate the number of electrons for material X. What do we have here? Here's our equation. NC, the density of states, is per cubic meter. But you only want it for 25 cubic centimeters. You have to modify this based on the sample size, right? Based on the sample size. So 10 to the 25, all right, per cubic meter. In 1 cubic meter, there are 100 centimeters cubed, right? So 100 cubed. That converts it to 1 centimeter, all right? We have 25 cubic centimeters, so we multiply that by 25, right? Minus 8.8 divided by 2 times Boltzmann's constant times 1000 plus 273, right? This is in Kelvin, so this should be in Kelvin, all right? And you'd find that N sub E was 951 electrons per 25 cubic centimeter, right? 950.9. You can't have a fraction of a particle. You can't have a fraction of an electron. You can't have a fraction of a proton, right? So you'd round this to the closest whole number, so 951, right? Which isn't a very big number. Material Y, the same thing, right? Per 25 cubic centimeters, we have a lower band gap now. We get 4.65 times 10 to the 13 electrons per 25 cubic centimeters. All right, so significantly greater number there. And for material Z, all right, the conductor, right? The conductor is material Z. Same thing again, but now we have this almost 0 band gap. And we get this, 2.39 times 10 to the 20 electrons per 25 centimeter cubed, right? So there were 3 main problems I ran into when grading this. Some of you ignored sample size and you calculated it per meter, which wasn't the question. Some of you recognized this, but you divided it by 25, which again, that was the wrong way to do that. And some of you thought this was negative 25. Don't know why, but then you got really, 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 really tiny numbers, like 10 to the minus 43 or something. All right, so we have this. So filled in here, 951, 465 times 10 to the 13, 239 times 10 to the 20th. So very different numbers here. Is X or Y an insulator, though? An electrical insulator. Materials. All right, you can look in the lecture slides for this. Materials with a band gap between 0 and about 3 eV. All right, so just above 0 to 3 eV or so. Those are typically semiconductors. All right, we don't say semi-insulator, we say semiconductor. Material X has a band gap of 8.8. So just going by that definition, it's not a conductor, it's not a semiconductor, it has to be an insulator, right? Just going on that, without even calculating the numbers, just based on how we split up band gaps, we would already know it's probably an insulator, a very good one too. Without knowing that though, right? If you didn't go back and look in the slides at band gaps and stuff, conductivity, what does it depend on? It depends on the number of conduction band electrons, right? And mobility, right? But we calculated the number of conduction band electrons. The conductor, or material Z, it had 10 to the 20 electrons. So I was to show you that a conductor has an enormous number of conduction band electrons. It's a very big number, 10 to the 20. Material Y was 10 to the 13. Yeah, it's 7 orders of magnitude lower, but that's still a pretty big number. And material X only had 951, which in comparison to 10 to the 20 is basically 0 electrons. You have no free electrons. So material X would be the insulator. It has a vanishingly tiny number of free electrons. Certainly way less than a conductor, and still way less than this material Y. Right? So X would be the insulator. That's what we would guess. Right. And again, you could also look in the slides again and find that something like aluminum oxide has a band gap of 8.8, and strontium titanate has a band gap of 3.4. 8.8 and 3.4. And you could look on this table here, you could find something like alumina. Alumina is in the insulator section, right? Strontium titanate is up here in the semiconductor metal region, right? There's been a lot of ceramics with very, very high band gaps. They are electrical insulators. They don't conduct with electrons. And those with 1 or 2 or 3 electron volt band gaps, they can be considered semiconductors, right? And given the right conditions, they will conduct, right? Now, electron conductivity and semiconductor. This is kind of an extension of the lecture. There's a bunch of slides here, right? Conductivity and Arrhenius behavior. All right. When you calculate it, so think back before the midterm. When you calculated the equilibrium number of Schottky defects in an ionic crystal, you had to know how many potential defect sites there were, right? How many vacancies can you have? Well, the maximum, the boundary is how many lattice sites do you have, right? What are the potential defect sites? That's the maximum number of defects you can make. You know, so if you have 10 potential sites, you can only have a maximum of 10 defects, right? So, you know, what about something like, you know, calculating the number of electrons in the conduction band, right? What's the maximum of something you might think about? It's the maximum number of electrons or bands or something like that. So An Arrhenius equation, it's often calculating an equilibrium number n out of a maximum number uppercase N of something, right? We're calculating some equilibrium or some maximum value, right, based on the theoretical maximum, right, modified by something like an activation energy and temperature. So N equals uppercase N as a function of something like activation energy and temperature. All right. For the number of electrons in the conduction band, we need to know not the maximum number of electrons that are possible in the sample, right? You might think, okay, we know what the material is. We know the atom. We know the number of electrons it has, and we assume that they all go to conduction. No, doesn't work that way. We need to know the maximum number of orbitals or states in the conduction band the electrons can occupy. The material has an enormous number of electrons, but they can't all go into the conduction band. We need to know the number of potential orbitals up there that they could squeeze into, or the number of states, right? That's why this N is the density of states, right? Or the density of electron, orbitals or bands or something up there that we could fill them up with. All right. So evolution of energy bands. All right. How the energy band gap arises in a nanoparticle. All right. Energy level. All right. We have an atom, and we have one band here an electron can occupy. And then we make a molecule. We take the two atoms, we stick them together. Well, if they're identical, the electrons would be violating exclusion if we just smash these two together. So one electron might go up in state, one might go down in state, right? So you see we get two bands here. Then we start cramming a bunch of molecules together, right? So we have all of these similar atoms with all their identical electron orbitals smashed together. And so we have to start creating more and more of these bands or these states where the electron goes up a little or it goes down a little bit, right? And so we start to see where this idea of a band gap comes from. We had some electrons going up and some going down to lower orbitals, right? And we have a whole bunch of closely spaced states that they could occupy, right? So as atoms are packed closer together, Pauli exclusion principle would be violated, right? You can't have two identical atoms overlapping their electron orbitals, right? We violate exclusion that way. To counter this, a greater number of orbitals with closely spaced energies are created. In a solid, we interpret the large number of orbitals as an allowed energy band, right? So it's allowed to occupy in here. There's a whole bunch of states in here, right? This was down below the gap. We care about the ones that are up here. What's the density of states up in the conduction band? How many little steps do we have? Each little step can hold an electron. So that's what that NC is. How many little bands are in there, right? So recall electrical conductivity. Sigma equals NEQ mu E, right? And NE was NC e to the minus EG over 2, or sometimes just KT, all right? And NE is often approximated as 10 to the 25 times that. And so you go, the density of states is approximately 10 to the 25 per cubic meter. Where does that come from? Right, if you look in the book, it just says 10 to the 25, and it doesn't say why. Where did it come from? Who made that number up? Right? And so you'd have to dig into physics books basically. You're getting into physics at this point. Solid state physics. All right. Materials engineers, we can apply simplified equations from solid state physics. But sometimes it's good to know where these things come from, right? To understand it's a simplification, right? Lots of equations you might run into are simplified. And if you don't recognize that, you might not, realize that there's more depth to it, right? That you can keep going further into an equation, right? Because you might only recognize this equation and you don't know it's simplified, right? And so 10 to the 25, it's kind of a simplification. Where does it come from? It comes from here. The density of states is approximately equal to the density of effective states here. 2 times 2 pi, and then a bunch of variables here. M sub E, effective electron mass. M sub H, effective hole mass. Think about that for a second. KT and H squared. H, Planck's constant. Remember that from high school physics? All right, so it comes from this equation. And you can do a unit analysis, right? You can do a unit analysis. If you just look at this and go, the density of effective states was per cubic meter. Per cubic meter. And we've got masses and electron volts and all kinds of fun stuff in here. And so you might just dump in units. You go kilogram, kilogram, Kelvin, Kelvin, electron volt, second, right? Okay, Kelvins go away, EV go away. What's going on here? What is this mess? And you get to play with this equation, E equals mc squared, right? To follow this through and figure out that, yeah, we get to per cubic meter. Again, this is something you don't really find in books. You have to do this yourself to see how it works. Right, so E equals mc squared, right? A kilogram can be equivalent to an electron volt per meters per second squared. Right? Think about that in materials. All right, so where does 10 to the 25 come from? All right, well, we have to think about the effective masses for electrons and holes. All right, and these are for various semiconductors, group 4, right? Group 3, group 2, that kind of stuff. Effective electron mass, effective hole mass. All right, the mass of an electron at rest. 9.1 times 10 to the minus 31 kilograms. The effective mass of an electron or a hole is the mass it appears to have in response to a force due to an interaction with another object. All right. So it has a rest mass, but it's moving really, really quickly, and it interacts with other particles, and it can have a mass which is slightly higher or slightly lower, right? And the same with the hole, the absence of the electron. And so we could go, okay, what's the effective density of states for silicon at room temperature? And we can dump in all of the numbers for silicon, right? So here's silicon, 300K, that'd be room temperature, 1.09, 1.15, right? 109, 1.15. And we get 3 times 10 to the 25 per cubic meter, or basically 10 to the 25. So in books, in a lot of materials engineering books, when you're calculating conduction band electrons, it might say in semiconductors, or it might ignore that, but they all have that value 10 to the 25. And that is for silicon, room temperature, a semiconductor. So that's where that number comes from. Someone just said, okay, semiconductors are mostly silicon, and we use them at room temperature, so we'll just use that as 10 to the 25. All right. But you could calculate something, you could do germanium. You could do the same calculation, and you get 10 to the 24. It's close, but it's not the same. Right. So this effective density of state, it can change. right? Orders of magnitude for different materials, right? So if you didn't realize that, and you started trying to calculate numbers like this just based on band gap energy, it'll show you a trend, but the numbers aren't necessarily accurate because that density of states is also a variable for each and every material. And a lot of books will simplify that because, well, yeah, this is getting really complicated all of a sudden, right? And you don't need to know that perhaps as, you know, a freshman student in an intro class, right? But you should be aware, a lot of your simpler books, the equations are maybe simplified, right, or dumbed down. And you should figure out if that's important to what you have to use them for sometimes in the future. All right. All right. Magnetic problems, the last bit here. And then I'll talk about what's on the final. All right. A coil of wire. Was it 0.3? It's 0.5 meters long. Yeah, it's 0.5. 0.5 meters long and having 500 turns, carries a current of 25 amps. Calculate the following: the value of the magnetic field strength, the value of the flux density. If a bar of chromium is placed in the coil, what is the magnetization M? The susceptibility of chromium is 3.13 times 10 to the minus 4. Show your work. B, the magnetization M within a bar of a metal alloy is 1.2 times 10 to the 6 amps per meter at a magnetic field strength H of 200 amps per meter. Calculate the following: magnetic susceptibility, the permeability, the flux density, and what types of magnetism do you think this material has and why? Right? You see something like that, it means it's not a one-word answer. It requires explanation. Right? And calculate saturation magnetization and magnetic induction of cobalt if it has a density of 8.9 grams per centimeter cubed and 3 unpaired spins per atom. All right. So a lot of this was examples in the lecture, right? Lots of these were just examples you could kind of look at and figure out what all the words meant and where they fit into the equations. And you could just play with some of the math, all right? And play with some of the units, because these units are, these are horrendous when you first see them. Especially if you're just used to like mechanical units. So, field strength, all right, magnetic field strength H, all right? I showed you this equation for an electromagnet, all right? So H equals I times N over L, all right? You can find similar equations, right? This is not the only equation to calculate this, because you might look and you might find a different equation and they use the variables differently and you can confuse yourself if you're not aware of that. So 25 amps times 500 turns divided by 0.5 meters, 25,000 amps per meter. All right. Flux density, B naught equals mu naught times H, all right? So you just calculated H, all right? Mu naught you can look up, all right? 1.257 times 10 to the minus 6 henries per meter times 25,000 amps per meter. Beta naught is 0.031 Henry amps per meter squared. A Henry amp is a Weber, and a Weber per meter squared is a Tesla. All right, so 0.031 Tesla. All right. As long as you had a unit that looks something like this, that was okay. They're all correct, but most people would just say Tesla. All right. Magnetization, M, equals susceptibility here times H. All right. Susceptibility was 3.13 times 10 to the minus 4 times 25,000 amps meter, 7.83 amps per meter. All right. So again, just like the example problems. All right. If they're daisy chained, right? You calculate one, you use it in the next problem, use it in the next problem, and so forth. All right. 3. Magnetization M within a bar of a metal alloy. It's 1.2 times 10 to the 6th amps per meter. At a magnetic field strength H of 200 amps per meter, right? So we've got some magnet here, right? With a field strength H of 200. And there's some bar. We put some bar of a metal alloy inside it. All right. We're gonna induce magnetism. Calculate the following. All right. The magnetic susceptibility, the permeability, U sub M, and the flux density, B. What types of magnetism do you think this material has? All right. So we know that magnetization is chi times H. We can solve here for susceptibility. It's just M divided by H. Right? Magnetization was 1.2 times 10 to the 6th. Divided by 200 is 6,000. Right? And this has no units. Right? It's just 6,000. Permeability. All right. Mu sub M equals mu naught 1 plus susceptibility. All right, we just figured out the susceptibility. So 1.257 times 10 to the 6th times 1 plus 6,000. Right. Permeability is 7.54 times 10 to the minus 3 henries per meter. All right. It's the same units as mu naught because susceptibility has no units. All right. Flux density. B, mu naught times 1 plus susceptibility times H, right? We know that mu naught 1 times 1 plus susceptibility is just U sub M, which we just calculated, right? So daisy chained. 7.54 times 10 to the minus 6 times 200, 1.51 Tesla, all right? Depending on how you rounded your numbers, you should have been pretty close. Some people made a mistake of just multiplying, I think, by like 6,000 or something. Again, the magnetic calculations can get confusing, right? Because there's a lot of very similar sounding variables and a lot of weird units that most of us aren't that familiar with. And so they're confusing at first, right? But if you have to work in this, you do more and more calculations, and it sticks in your head after a while. Right? A little more complicated than mechanical properties. Last problem here, problem 3. No. It's part D. Part D. All right. What type of magnetism do you think this material has and why? All right. So magnetization, susceptibility, permeability, and flux density. Right. We can look at these numbers and compare them to some in the book, right, or some in the lecture slides. And we see that the susceptibility is much greater than 1, right? So there was that graph, right, where you had vacuum, right? It was like B and H, something like that. Right, you had paramagnetic and you had diamagnetic. Right? Vacuum, the susceptibility is basically 0. Diamagnetic is just below, negative, and paramagnetic is just above, positive. But both of them around 1, right there, 10 to the minus 6, or 10 to, they're tiny little numbers, right? And so we have a susceptibility much greater than 1. So we can eliminate diamagnetic and paramagnetic, right? Because those are typically way less than 1, either positive or negative. right? The material also has a large magnetization, right? It's been magnetized. So it's not antiferromagnetic. Antiferromagnetic doesn't have net magnetization because the dipoles, they cancel out, right? They cancel each other out exactly. High susceptibility and magnetization and permeability would indicate it's either ferromagnetic or ferrimagnetic, right? Being that it's a metal alloy, it's probably ferromagnetic, but we'd probably have to know a little bit more, right? We could guess ferromagnetic, right? But if you just say because it has a high susceptibility, well, it could also be ferrimagnetic, right? If you say ferromagnetic because it's a metal alloy, okay, I could buy that. All right, so you could say ferri or ferromagnetic, or ferromagnetic if you could say, you know, something about it being a metal. That would make sense. All right. Problem 4, there we go. Calculate a saturation magnetization, M sub S, and B, the magnetic induction, B sub S, of cobalt if it has a density of 8.9 grams per centimeter cubed and 3 unpaired spins per atom. Show your work. All right, again, an example from the lecture slides. All right, M sub S equals N sub V, N sub S times mu B. N sub V, the number of atoms per unit volume. N sub S, the number of unpaired spins per atom, 3 for cobalt in this case. And mu sub B, the Bohr magneton. All right, so a constant. 9.27 times 10 to the minus 24 amps per meter squared. Now, we know N sub S is 3. Mu B is a constant. So we need to know the number of atoms per unit volume, N sub V. Now, some of you just copied the number right from the slides, which was for iron. And it's close, but it's not exact. What's the number of atoms per unit volume? That's a calculation you did months ago, if you remember it, with the equilibrium vacancy calculation. To figure out the number of potential, you know, defects, you need to know the number of atoms that were in the sample, right? So that was Avogadro's number times density divided by molar mass. All right. Iron and cobalt have different densities and molar masses, right? If the ratio is similar, so be it. But it's not going to be exact. The number of atoms per unit volume is different for a given material because the density and the molar masses are different. All right. So 6.022 times 10 to the 23rd times 8.9 divided by 58.93. That is the molar mass of cobalt. Some of you, I think, cut that in half for something. Maybe you thought it was diatomic. I don't know. But it wasn't like 26 that some of you had, or 28. As you get N sub V, 9.09 times 10 to the 22 atoms per centimeter cubed. Atoms in centimeters cubed, atoms per centimeter cubed. Or 9.09 times 10 to the 28 atoms per meter cubed. All right. Bohr magneton, that's in meters, right? That's in meters. So you can't go mixing centimeters and meters. It won't work. So calculate the saturation magnetization now. All right, we calculated NV. All right, we dump in the numbers. All right, 9.09 times 10 to the 28th atoms per meter cubed times 3, which a whole bunch of people forgot to multiply by 3. I don't know why. Or some of you multiplied by 0.6. Again, I don't know why. But yeah, you can't forget that. Times the Bohr magneton, which is 10 to the minus 24. All right. You get here 2.53 times 10 to the 6th amps per meter. All right. Calculate B sub S, magnetic induction. V is mu naught 1 plus susceptibility times H. All right. When the susceptibility is much greater than 1, we can just ignore the 1. Go back here. We had, 6,000 plus 1. Does multiplying something by 6,000 or 6,001 make much of a difference? Not really. So if it's a really big susceptibility, you can just ignore that 1. Right? So you get B is approximately equal to mu naught X times H. And M is X times H. So saturation here is mu naught times M sub S. Right? We can get rid of that susceptibility that we don't know. And we get this, 3.18 Tesla. 3.18 Tesla. All right. Now, the last little bit here I'll mention, measurement of magnetic properties. These are calculations and stuff, right? How do you actually measure some of this? How do you measure some of these properties? Right? Electronic properties, you can use a multimeter and measure, resistance and stuff. But how do you measure like magnetization or susceptibility or that stuff? What do you use to do that with? All right. So to measure magnetic properties, right? First, you need a way of generating a magnetic field, right? You need to be able to make a magnetic field, and you need to measure the induced magnetism, all right? So we need to make a field and understand its shape and all that stuff. And then how do we actually measure the induction, all right? So magnetic fields can be generated from solenoids, electromagnets, or permanent magnets, all right? So a solenoid, that's just a bunch of wire wrapped around an insulating tube. Right, so you have like a hollow pipe, and you just wrap that with wire, right? That's a solenoid. An electromagnet is a wire wrapped around a solid core, like a piece of iron. Right, so you have an iron nail. You wrap that with wire. That's an electromagnet. If it's just hollow, it's a solenoid. All right. So field strength, electromagnets approximately equal to solenoids. Both of them are variable, but both of them can produce much stronger magnetic fields than permanent magnets. All right, so a lot of magnetic fields are generated with solenoids, right, or electromagnets, because they're very strong, as opposed to a permanent magnet, right? For experimental work, electromagnets and solenoids are the most useful, right, because they can generate variable magnetic fields, right? We can turn it up, we can turn it down, we can turn it backwards, so we can study, hysteresis behavior and things like that too. Now, how do you measure a magnetic field? All right. A magnetic field can be measured using a device called a magnetometer or a Gauss meter, right? Or a Gauss meter. People say it differently depending on what country you're from. It's a Gauss meter to me, right? Magnetometer or a Gauss meter. They can work based on a few different principles. Right? The Hall effect, right? That was in the slides, right? You can use the Hall effect where a voltage is generated by the magnetic field, right? You can use magnetostriction, in which the resistivity is changed by the magnetic field strength, or magnetic induction, in which a moving magnetic field induces EMF in a coil. Right? So there's different ways to measure this based on, resistivity changes, voltage voltage induction, stuff like that, right? Or EMF. Hall probes. Hall probes, based on the Hall effect, can measure a steady or changing external magnetic field. Flux meters, based on induction, measure changes in the field strength or need to be moved in order to measure a steady field, right? So depending on if your field strength is fixed or it's going up and down and oscillating, right? There's different ways you have to measure that because different effects, they require steady field or moving field, all right? So something like susceptibility now. How do you measure susceptibility? Right, this is an older technique. Right, susceptibility can be measured using, how do you say this guy's name? It's a French guy. We'll say GUI. The GUI technique, or variations of it, which are force balance methods. So what do we see here? We have a magnetic field, right, running this way. We have our sample. We have our sample this way, right? It's on a balance. It's on a balance beam, right? So that there's a mass here. So we have our sample, we have our counter mass, and they're balanced. The sample's put in a magnetic field, all right? It's either going to be pushed up if it's diamagnetic, or it's going to be pulled down if it's paramagnetic or anti-ferromagnetic, actually. So it gets pushed up or pulled down. There's going to be a force acting on it, right? And from that force, right, we can end up figuring out susceptibility, right? We have delta mg A times h squared. So we have to add or subtract mass to rebalance it. So it's balanced. We turn on the magnet and it moves up or down. And we have to rebalance it by adding or subtracting mass to the counter. And from that, you can figure out susceptibility. All right? And there are other techniques you can use to measure things like M and B in permanent ferro and ferri magnets. This only works on para and diamagnetic, basically. All right. Experimentally, magnetic moment. Magnetic moment. With a measure of susceptibility or permeability, the magnetic moment mu can be calculated. All right. So susceptibility, right, for some unit volume, right, the susceptibility V equals M over H, right? Here, this is where you might need to know the density, right? If you divide that by density, all right? And you see here, you see this equation here. Right, so you have some susceptibility divided by density. You get this one here, Na mu naught mu squared. All right, atoms per unit volume, vacuum permeability, Avogadro's number, yada, yada, yada. All right. That's not what I wanted to show. Okay. So here, calculate the magnetic moment for oxygen. Now, did I show this down here? Oh, I didn't. I should have gone back and put that one in there. In a magnetic lecture, and there was a table with magnetic moments. And there are magnetic moments which you can measure, and those which are theoretically calculated, right? How do you theoretically calculate those things? That's what this is. Calculate the magnetic moment of oxygen. The measured susceptibility, all right, the measured susceptibility of oxygen, X sub m, 1.36 times 10 to the minus 6 meters cubed per kilogram. Determine the magnetic moment mu. All right, we had that equation. Rearrange for mu. Oxygen is diatomic. That's where that is important. And you can get this. 2.85 times the Bohr magneton per molecule, right? In that table, it was numbers like 1 and 2 and 3, right? That's times the Bohr magneton per molecule. Right? It's probably not good slides for freshmen. Right? From quantum theory, the effective magnetic moment of an atom, mu sub f, is calculated this way. So this was experimental. This was experimental. And this is calculated. And this is where you get to use quantum numbers again, right? You get these, remember this from the magnetic lecture, all right? I don't actually want to go into this because this is a real headache, this stuff here, all right? But yeah, when you get into electrical and magnetic properties beyond, an introductory book, it gets a lot into solid state physics and quantum mechanics, stuff that you, as an engineer, you go, why on earth would I ever have to use that stuff? Well, you have to for properties involving electrons and electrons moving around, right? Generating magnetic fields and stuff like that. That actually gets into solid state physics and quantum mechanics, right? As you can see here, there's a graph here, right? We might have, what might we calculate, right? And what kind of stuff can we measure and approach to that? And why are there differences? Why is what we measure different than what we predict theoretically, right? That's getting into the hardcore physics of it. All right, that's enough of that. All right, final exam info. What are we at here? 3 o'clock. All right, not too long. All right. This is of more use for freshmen than upperclassmen, I suspect. All right. All right. This test is next Friday. I think that's December 4th. Yeah. Next Friday, December 4th at 9 a.m. until 12. It's a 3-hour exam. This exam is in 5 or 6 different classrooms because it's a big class. I don't know what room any of you are in. You have to look that up, right? When you look up your test schedule, it will tell you what room you should be in. But it is December 4th at 9 a.m. All right. You have to be prepared, right? It's a real exam, right? You're going to sit down and take a paper-based exam here. So be prepared, right? Have a pen or a pencil. For my exams, you're maybe going to make mistakes. So bring a pencil probably with an eraser, right? Or a whiteout if you're using a pen. You should have a ruler, right? Because you might have to draw lines. You should have your calculator. And you should have your student ID card, right? At a minimum. All right. For freshmen, and this is more relevant to the inter students, if there are any, you have to have a scientific calculator. You can't use graphing calculators, which some students from other countries do. You can't use them. You have to use a scientific calculator. Here's a list. Pretty much everyone in school has a Casio, which you can buy at the bookstore if you don't have one. All right. Again, for freshmen, you have to wear your student uniform, right? You have to wear a student uniform. You can't wear whatever you want. There are rules about this stuff. Some proctors in the room won't let you in, right? Each exam is proctored by 2 or 3 professors you've probably never met. It's usually random, right? They don't know you, they don't care. Some of them like to be a pain if you're not wearing a uniform, if you're not tucking your shirt in, stuff like that. So wear your uniform, all right? And have your ID card ready because we usually check them when you come in the room. If you don't have your ID, you won't be allowed to take the test right away. You have to go get a printout of your ID card and all that stuff. So don't lose it. Because if you do, you got to go to the registrar and get a piece of paper and all that. It's a lot of fun. So don't forget your ID, your student ID, all right? You have to be on time, right? The exam starts at 9. Don't try to show up more than 20 minutes late because you won't be let in the room without going to get a note from the test center, right? Where they distribute the test from. They'll make you go there and get a note and all that saying you're late and stuff, and it's a waste of time again. So you can't be more than 20 minutes late, all right? After 1 hour, you're not allowed to take the test, right? So if you get stuck in traffic and you show up 40 minutes late, you have to get a note and hope you get there before an hour, right? Because after 1 hour, you're allowed to leave the room. The test is you're allowed to leave the test after 1 hour, all right? So if you're done within an hour, you can then leave, all right? But before that, you can't. So that's why you can only be an hour late. All right, so that's for the freshmen. The seniors know all this stuff. So uniform, ID card, be on time. You can leave after 1 hour, even if it's 3 hours. After you leave, you can't go back, obviously. All right. Cool. All right, so about the exam now. It is 9 questions worth 10 points each. All right. When you get your test and you sit down, right, your test is on the table already, and you sit down, you should look at your test and make sure all of the questions are there. All right. Because sometimes you might be missing a question, or you might have 2 of the same questions. So check your exam. All right. Each page is numbered. Right. You should have 1 through 9 questions. 1 question per page. Some questions have multiple parts, like A, B, and C, right? Answer as much of it as you can, right? Because there's partial credit, right? If you leave it completely blank, that's easy to grade. I just go 0, right? But if you attempt to do something smart, I might give you some credit for it, all right? The types of questions you should expect. There's some writing, right? Not like essays, right? But you might have to write a few sentences or a paragraph here and there. Multiple choice, graphical and math problems, calculation problems. It's closed book, all right? No notes, no books, no dictionaries. It's whatever's in your head, all right? Now, while I was talking, somebody lined me a question. Who was that? All right. Do you give the formula on calculation part, or do I have to remember it? I will give you a complex equation, all right? So something like the Beer-Lambert law with reflection, like I would give you that equation. I remember it, but you guys won't, right? So this was what I call complex. So I give you that, but you should remember a simple equation like Hooke's law or density, right? That's the kind of stuff you should remember. Simple little equations. If it has an exponential in it, I would give it to you, all right? So just remember simple equations you already know. What do you study? All right, it's pretty obvious. Study the lecture slides, all right, if the lecture is going to be on the test. Study the example problems, right, and study the worksheets I've given you and all those solutions, right, because the test questions would be very, very similar to a lot of that stuff. What should you study or expect on the test? It covers lectures 8 through 13. The last lecture was lecture 14, so that's not on the exam. So that material selection stuff, don't study it. It's not on the test. So it's going from what, metal, ceramics, polymers, and then all of the properties. All right, those are those lectures. There's a question on Hall Petch behavior, a question on ceramic batching, a question on polymers, 2 questions on mechanical properties, a question on optical properties, a question on thermal properties, and some questions on electrical and magnetic properties. All right. Knowledge might be stuff like multiple choice, right? Or writing a paragraph or 2. A calculation is a math problem, like a worksheet, right? So you have 1, 2, 3, 4, 5 math problems. 1, 2, 3, 4 knowledge type questions, multiple choice or writing questions, things like that. All right, so if you don't see it here, right, then you don't have to study it, right? So you don't have to study material selection. That's not necessary. All right, but something like polymers knowledge, that could be anything in the lecture, right? That could be any of the knowledge in that lecture you might have to recall. All right, so it's not necessarily simple. You might have to know quite a few things. All right, but the calculations are perhaps things you've already seen. All right, so that is the end for today. That's all I wanted to talk about. All right, I'll put this file in Teams in a second. All right, let me stop sharing here. Are there any questions? Are there any questions? Where is that file? Turn that off. I'll turn that on. Files. Files. Not that. Files. Class materials. Final exam info. Go there. Close that. Open that. Oh, where the heck did you go? Oh, so annoying. All right, so there you go. There's the PDF on what you should study, right? All of the worksheet solutions are in the folder, right? You have all of the lectures already. So study, 8, 9, 10, 11, 12, and 13. All right. Stop sharing. All right. If there are no questions, that was the end for today. And the last time we'll have a meeting, I suppose. All right. After you've taken the exam, I'll get all the copies back and I'll have to grade them. And then the grades will be submitted online to New ACES or whatever, and you'll get your grades online. But that takes a while. The departments have to have a meeting. Engineering faculty has a meeting. All the grades get approved and all that stuff. It takes a while, right? So don't expect your grade like the next day, right? Expect it in a few weeks. All right. So if there's no questions, I'm done. All right. So let me stop recording now.